In this lesson, we discuss about scalar and vector fields and operators that act on these fields. What do we mean by scalar field? Simply a scalar function of position, and the function of position can represent some physical quantity such as temperature, pressure, or potential. Whereas a vector field is a vector function of position in which the physical quantity is a vector, for instance, velocity, electric field, magnetic field. We can represent graphically these fields in several ways. For instance, for vector fields, you can plot the vector together with its direction, its magnitude, for some points of space. On scalar and vector field, we can operate in some way. For instance, with vector fields, we can multiply a vector field times a scalar. We can multiply a vector field times another vector field with a dot product. The result is a scalar, and the value of these scalars is the product of the magnitude of the two fields, of the two vectors, times the cosine of the angle between the two vectors. So that this product, this dot product, is maximum when the two vectors are parallel, and is null when the two are orthogonal. We have the cross product, which is indicated in this way. The cross product between two vectors is a vector. The direction of this vector is perpendicular to the plane of the two vectors A and B. The magnitude of this new vector C is the product of the two magnitudes of the two vectors times the sine of the angle between them, so that the maximum value of this cross product happens when the two vectors are perpendicular to each other and is zero when the two are parallel to each other. Let's introduce now some integral operators. One is the flux. It's indicated in this way. We can have an open surface, for instance, with an oriented normal unit vector in some direction. We compute the scalar product of our vector field times the normal unit vector, and we integrate over the whole of the surface. This is the flux of vector A through the surface S. If the surface is closed, we indicate this flux with a circle on the integral simply. The flux is a measure of the flow of the vector field through the surface in the direction of the normal unit vector. Another important operator of integral type is the line integral or circulation. So we can define in space a line from P1 to P2 oriented, and we can compute the dot product between A and the differential on this line, integrating from P1 to P2. This is a scalar, therefore, and if it is closed, again we indicate this integral with a circle on the integral sign, and we call the result circulation. So what is the circulation actually? It's a measure of the rotation of our vector field around the line in the direction of the line itself. The first differential operator that we define for scalar fields is the gradient. So we start from a scalar field, a function of position at each point of space, and we compute the gradient by this definition. We obtain therefore a vector field whose direction is along the maximum increase of the scalar field in space. So at each point we have a vector that is, as you've seen in this picture, perpendicular to the equisurfaces of our scalar field phi. There are some properties for this gradient. For instance, the line integral of the gradient from P1 to P2 along a line, whatever line, equals always, independently of the line, the difference between the value of the potential of the scalar field phi between the endpoints and the starting point. So it is independent of the line, only depends on the starting and ending points. A simple derivation from this is the fact that if the line is closed, the line integral, the circulation of the gradient of an arbitrary scalar field is always zero. Another important operator is the divergence. The divergence is obtained as follows. We take a closed surface and we compute the flux of our vector field through this closed surface. This closed surface is the boundary of a volume omega. So we divide our flux times omega and we make the limit as omega goes to zero around a given point of space. This is the definition, which is independent of the coordinate used, of the divergence of A. So as you see, the divergence is actually a density of flux. Its expression in Cartesian coordinates is the following one, and the various quantities are shown in this picture. Associated to the divergence, there is the important divergence theorem that states that the total flux through a closed surface of a vector field equals the integral volume of the divergence of A, the same vector fields, through in the volume whose boundary is the closed surface. Another important differential operator is the curl. So we identify a line, a closed line in space, which is the boundary of an open surface, and we compute the circulation of our vector field A through this line. We divide the result by the surface S, the area of the surface whose boundary is the line, the closed line, and we make the limit, the surface going to zero, of this computation. What we obtain in this way is a component of the curl of A along the direction normal to the surface itself. The line direction and the normal to the surface are linked by the right-hand rule. The various expressions of the curl in Cartesian coordinates are shown here. So the right-hand rule is shown also in this picture. As you see, we run around the line, and by the right-hand rule you obtain the direction of the normal, or vice versa. We indicate first the normal, and we obtain consequently the direction along which we compute the circulation. An important theorem associated to the curl is Stokes' theorem. It says that the total flux through an open surface of the curl of A equals the circulation of A around the boundary of this surface. And since the circulation of A on the boundary of the surface is independent on the actual surface but only on the boundary, we have also that the flux of the curl of a vector field through an open surface is only dependent on the boundary on the surface. If the surface is closed, clearly the total flux of the curl of A is zero. We can also have second-order operators, obtained by applying twice our first-order operators. For instance, we can apply the divergence to the gradient, and the result is the Laplace operator, or Laplacian. It's very important, for instance, in electrostatics. We can apply the curl to the gradient, and we obtain zero, because it's an identity. The curl of the gradient is always zero, independently of the scalar field phi. We say for this reason that phi is irrotational, no curl, gradient of phi, sorry, and also a name is conservative. We can apply the divergence to the curl of A, and we obtain identically zero also in this case, and if a field has zero divergence everywhere in space, we call this field solenoidal. For this reason, the curl of A is solenoidal. Then we can also have the curl of the curl, which is a second-order operator that can be written as the gradient of the divergence of A minus the Laplace operator applied to a vector field A. In this case, this can be seen as the definition, independent of the coordinate system, of the Laplace operator applied to a vector field. In addition to the well-known Cartesian coordinate system, there are other two very important coordinate systems. One is the cylindrical coordinate system, the other is the spherical coordinate system. In the cylindrical coordinate system, the various quantities are shown here. We have the three variables ρ, phi, and z, and the corresponding unit vectors, and the various range of definition for these variables, and they are shown here. In the spherical system, the three variables are r, theta, the angle with respect to the z-axis, and phi, the angle of the projection of the point on the xy plane with respect to the x-axis. Also in this case, we have a set of unit vectors and the range of the various coordinates. For the coordinate cylindrical and spherical are the most common one. There are other coordinate systems that are not used in this course.